Welcome back. Now we will go to the formation of NOx. Okay. Now, as we discussed, of course, we need to understand ignition delay, but also because that is very critical in determining whether in a given combustor you will have reactions or not at all, whether that given combustor that you have designed, whether there is sufficient flow residence time scale for your reaction to happen. Of course, your flow residence time scale has to be much bigger than the chemical time scales, and the chemical time scale is characterized by the ignition delay time scale. Of course, you have to guarantee that. So, it is important to understand where does the ignition delay come from and where is your initiation and present branching and heat release reaction come from. But at the same time, you have to design a combustor of an aero engine in such a way that it produces very little emission in terms of there is very little emission of pollutants, and one of the biggest pollutant is NOx, which is NO, and NO2 is represented in general by NOx, x is equal to 1 or x equal to 2, and also there is nitrous oxide N2O. Okay, now these are very bad because it creates smog, and it is really very unhealthy, and we need to understand the reaction mechanisms that gives rise to this. Now, before we go into this, there are essentially three mechanisms. There are essentially three mechanisms of NOx formation. One is called the Zeldovich mechanism, or the formation of thermal NOx. The second is the prompt NOx, and the third is the nitrous N2O route. So, using these three we can describe essentially the formation of NOx in a very comprehensive manner. So, what is the first route, which is the most important as discovered by Zeldovich? What is thermal NOx? This is called it is obtained by the Zeldovich mechanism. So, what it says is that the most important step, which is the first step, is when N2 is attacked by an oxygen atom and it forms NO and N atom. Okay. Now, this is the most important thing, and then the N atom can react with oxygen to form NO and O, and then this N and OH can essentially form NO and H. Alright. So, the first reaction is the most important reaction, where N2O reaction is strongly temperature sensitive, and it is also the rate limiting mechanism, because it is very difficult to break the NN bond, and the NN bond can be broken by an oxygen only at very high temperatures. Okay. And as a result, this mechanism is this path is important only at very high temperature of 1800 Kelvin, and it is the thermal NOx is mainly the product or NOx that is formed in the product. But then it was found that and of course, we see that there is no much dependence of oxygen, because it depends on the oxygen radical as such. Okay. But then it was found that that NOx is also formed in colder part of the flame, and it does not need always high temperature to be formed, and that leads to the discovery of this prompt NOx mechanism by Fenimore. And this reaction between, essentially it is a reaction between nitrogen and hydrocarbon radicals, and it follows this, that N2 essentially reacts with CH to form this NCN molecule, an H atom, and then it goes through this NCN, essentially goes through a different kind of NCN, then essentially also this N2 and CH2 also conforms HCN and NH, and this HCH and NH thus conformed can go through different kind of steps. It can be attacked by oxygen, but the most important thing is that all this lead to the formation of N. Why the formation of N is important? Because once N is formed, you can basically can react with oxygen to form NO plus O, or it can react with OH to form NO plus OH. So, the formation of N is the most challenging part. It can either happen through the prompt NOx mechanism, or it can happen through the thermal NOx mechanism, where N2, the thermal NOx, if you remember, there is N2 plus O goes to N2 plus O goes to NO plus N. Yes. So, N2 plus O essentially goes to NO plus N. So, this was the thermal NOx mechanism that we just discussed. Now, also you see that these also this prompt NOx mechanism is also promoted with increase in temperature, and also it needs the presence of the hydrocarbon molecule actually. Now, the N2O route that we discussed is essentially this is a third body reaction, three body reaction, where N2 plus oxygen atom can react in after being attacked by or can be when a third body also comes in, and this N2O is formed. This N2O then can react with NO to form two molecules of NO. So, this is the other mechanism by which this is formed. Now, control of NO, I will not go into this. There can be different methods by which NO can be controlled. It can be done by exhaust gas recirculation, and it can be done to promote mixing, as in HCCI engines, where of course we can go to a premixed flame mode, as we will see that when the temperature can be reduced, at least then the thermal NOx can be reduced, and then we can use water injection, because the water can they reduce temperature and produce O atoms, and the O atom can be taken to form which is essentially this O atom that is present in this reaction mechanisms that is formed, essentially goes and attacks the N2 to form the thermal NOx. So, if you can take away this O atom by reaction with water to form 2H, you basically cut off this thermal NOx mechanism. Also, you can do stage burning, fuel rich followed by fuel lean, and there are different other processes by which reburn, cell-safe catalytic reduction, and rapid reduction of NOx, etc. These are the methods by which NOx is reduced. Now, next pollution formation is essentially this soot formation. This, as you know, this hydrocarbon combustion, when it happens in rich flames, it gives rise to this particulate carbon or soot. Here you can see that this from this aircraft engine, this amount of soot is coming. Of course, nowadays aircraft engines have improved, and this amount of soot is rare, but still we need to understand there is still substantial soot being formed, because in many aircraft engine combustion happens in non-premix mode, and we need to understand the mechanism by which this soot is formed. So, this yellow luminescence that you see is essentially caused by the thermal reduction of soot in flames, or thermal radiation of essentially the soot in flames. Soot are essentially black bodies, and it radiates over a large range of the over a huge range of the visible spectrum, and it gives out this yellow color that we see. Okay. Now, soot is not a uniquely defined chemical substance, and it is mainly composed of carbon, but it also contains some amount of hydrogen, and the atomic C/H ratio is about 8:1, and the mass density of soot is about 2 grams per cubic centimeter. Now, why does soot is formed? The soot is essentially you will see that soot is a agglomeration of large number of carbon, small carbon particles, and these carbon particles are essentially composed of several thousands of carbon atoms, and these carbon atoms can also have different kind of very layered kind of structures, which are and this understanding and the mechanism by which soot formation and the structures of soot is an active research area in combustion currently. And as we discussed, this chain like aggregates of spherical particles are formed, and they contain several thousands, hundred thousands of carbon atoms, and diameters of these particles are from 20 to 50 nanometer. And the mechanism of soot formation, there are two steps essentially, or it can be subdivided into two sets. The most important thing is that one of the most important soot precursor is acetylene. So, acetylene essentially you will see that acetylene, the C2H2 can go to different go through all these steps, and essentially it leads to this formation of this cyclic aromatic compound, and then it leads to benzene. This benzene formation pathway is a very important thing. So, acetylene, whenever there is acetylene, there are this through all these steps it can go to formation of benzene. I will not go into the details of the steps here. And then there is also something called precursor to soot, which is called polyaromatic hydrocarbons, and so fuel rich combustion produces acetylene, and then acetylene leads to polymerization and formation of this polyaromatic hydrocarbons, which is just we discussed. So, whenever there is acetylene, whenever there is fuel rich combustion, it essentially leads to formation of acetylene molecules, and acetylene molecules leads to this formation of this benzene rings, and what happens is that essentially the methylene radicals from burning long chain aliphatic fuels due to reaction between C2H2 and O atom and directly related to acetylene. And also in fuel rich conditions, methane or natural gas flames are methylene radicals produced from direct reaction between CH3 and OH. That is also the thing. And then how does the aromatic grow to form soots, because the soot is not essentially a benzene ring, and that is governed by this Hakka mechanism, which is called hydrogen abstraction by C2H2 addition, the Hakka mechanism. So the thing is that whenever there is a, so we have seen that acetylene leads to the formation of this benzene molecule, and then this benzene molecule can be, there can be a hydrogen abstraction from this benzene molecule, and then we have this free radical, and this we essentially can have an unpaired electron, and this unpaired electron can latch onto an acetylene. And now when you know that whenever there is an acetylene, there is also a mechanism by which it can form this benzene ring. So this benzene ring forms latches onto the another benzene ring, and so on and so forth. And you can see by this mechanism, by this hydrogen abstraction from this benzene ring, and then latching onto that position of this unpaired electron by the acetylene, essentially leads to growth of this benzene ring side by side, and that is the hydrogen abstraction by C2H by acetylene, or the Hakka mechanism of formation of polyaromatic hydrocarbon formation, and these are essentially the soot precursor that is being formed. Now so this is this thing that is important in the formation of soot. And of course it can, depending on the neighboring ring structure, as you see that this newly formed ring can either grow radially into acetylene, or it can grow to, it can be activated through hydrogen abstraction reaction to produce a polyaromatic hydrocarbon radical species. So this is the thing that we talked about right now, that if we have a benzene molecule, and the benzene molecule can arise from itself from acetylene, and then also it can grow to another path where it can form another alternative polyaromatic hydrocarbon growth formation, in which you have this kind of shapes instead of this side by side shapes that we just discussed. So both of these different structures can be formed by from a benzene ring, and then through different variants of the Hakka mechanism. So I will not go into the details in this one. So now on the final topic of this oxidation mechanism of fuels, we would like to discuss mechanism reduction. Now of course you have seen, you have by now understood the importance of detailed reactions, and we have understood that to predict important quantities like ignition, delay, etc. of practical fuels like N-dodec, which is an aviation turbine fuel, which is essentially representative of an aviation turbine fuel, or Jet A. We need a detailed reaction mechanism because it involves all these different steps. You need to understand how this fuel molecule breaks down, how it can lead to this chain branching reactions, and then how it can essentially compete with this other reactions, and then when those reactions can go down, other reactions can go up, and these leads to different kind of complicated things or observations like ignition, delay, etc. Okay. So to predict this, of course we need detailed mechanisms, but then the problem is that the detailed mechanisms are very large. Okay. It can range, as we see, it can range from 10 to 10,000 species, and it can range from 10 to 10 to the power 4 reactions. That is, there can be 10 to 1,000 species. For example, the smallest reaction mechanism, detailed reaction mechanism that we have seen is that of hydrogen, which involves 9 reactions, 9 species, 19 reactions, and the large ones, for example N-dodec, can involve very large number of molecules, very large number of species, and very large number of reactions of the order of 1,000 species and 10,000 reactions, and the reactions and species are essentially related by this k to the 5n. And in this diagram, if we plot species on the x-axis and number of reactions on the y-axis, you see that for all things here we see that this is GRI 1.2 on this methane air mechanism that involves about, say, 20-30, about 30-40 species and more than 120 reactions, whereas this C16 or this For example, the C12 which we are discussing, this N-dodecan, that involves about 1000 species and about 9000 reactions. Okay. Of course, if you want to do a detailed CFD, if you want to solve for or want to predict or want to validate combustion inside a practical engine, one cannot use so many species actually in a practical CFD code. One cannot use 1000 species and one cannot use 9000 reactions if you want to solve for combustion of jet fuels. So, or even which is not even jet fuel, but the representative of the jet fuel, which is N-dodecan. So, what you do is that of course, it computes with the flow description and it limits the accuracy of both, and in here this detailed reactions inhibits the feasibility of computing even for phenomena of a really large, even for simple phenomena like computing ignition delay, etc. You have a this becomes really too large, and even for a simple phenomena like ignition delay, and forget about computing for detailed turbulent combustion in an actual engine. Okay. So, we need essentially simplified mechanism with minimal loss of comprehensiveness and the dependence of temperature, pressure and phenomena concentration phenomena, and it should be accurate. It should be able to predict things like ignition delay, laminar flame speed, extinction strain rate. We will see what these are essentially, but you know already what is ignition delay. It should be able to predict ignition delay at least to a reasonably accuracy, and so these are the requirements. So, this is the once again the detailed this diagram proposed by Lu and Tianfeng Lu and Professor C.K. Law, and you see that once again it can range from this to this. A very large number of species can be get involved as the complexity of the fuel increases, C8, C12, C16, this sort of things. So, mechanism reduction, the requirement of a comprehensive mechanism is that it must be accurate and must be able to reliably describe the combustion phenomena, and it has to describe all kinds of combustion phenomena over possible ranges of thermodynamic parameters, that is T, temperature, pressure and Y, species mass fractions. The three factors that are responsible for mechanism reduction are essentially computational power and stiff system of equations, because you see all this EA by RT with this reaction rate is different kinds of EAs gives the different time scales for reactions. So, that makes this this differential equations of this things species quite stiff system, and it is complicated, and we have to basically identify the dominant species and the pathways and the coupling between the reactions and the species. Okay. Now, for example, of course the most simple reaction one can think of is the one step. This is CH4 CO2 plus H2O. Now, of course, you see that we have already known by now that CH4 does not go to CO2 in one step, and even CO2 cannot be formed in one step even from CO. So, we need to have a CO in there is the CO oxidation is of course the most important reaction in one of the most important reactions in hydrocarbon combustion, because that is the key step where heat is released. So, it is natural to introduce CO into the reaction, but of course, these are not actual reactions that happen. These are just lumped, these are just adding some more details onto our global reactions by including one step species. So, of course, we can here we include the 3 steps where we again include now hydrogen, because hydrogen is also an important step that is formed, and then we can have once again an approximate reaction where we have a detailed alkane or a complicated alkane of CmH2m, and we can have which breaks down into basically ethylene, and then this ethylene reacts to with oxygen to form the CO and H2, and then CO goes to from CO2 and a hydrogen is oxidized to form water. Of course, as you know that none of these reactions actually happen like this, but these just adds little more details into a one step reaction mechanism, okay, and it considers this important species important intermediates like CO and H2. But of course, to describe this in details you would need a few thousands of species and thousands of reactions if say M is large, and so this is a trade off essentially. So, the idea is that you only consider this was, but this was like done in an ad hoc manner. Okay. So, we think that that CO is important, we think that H2O is important, we think that ethylene is important. So, that is why these have been done in an ad hoc manner, but to do it systematically we can consider this we can consider elimination of unimportant species by using this directed relation graph or the DRG. Okay. And this can be also done by lumping, that is by applying quasi steady state species and this partial equilibrium assumptions, which has gone also by considering similar diffusivities. So, the theories of mechanism reductions, if we see that there are like detailed mechanism to skeletal mechanism reduction has been in people have been active in this area for quite some time. This is the main reason, because people realize that on one hand, if you use one step global reaction mechanism, then you get erroneous results. You cannot predict many things. On the other hand, if you want to use the complete detailed reaction mechanism, you get you run out of computing power and you run out of memory. So, people try to find out methods by which detailed to skeletal mechanisms can be formed, at least by several of these techniques like sensitivity and Jacobian analysis, detailed reaction, and computational singular perturbation called CSP, and directed relation graph, these things. So, we will just and then subsequently you can reduce by employing partial equilibrium assumption and quasi steady state species concepts. So, what is DRG, directed relation graph? So, we think that we consider the reaction, a detailed reaction, we represent the species by this alphabets A, B, C, D, and if the species A and B are reacting, we produce we make an edge between them. So, with a directed edge, that is A goes to B if it is like that. Okay. And if it is if in the reaction between A and B, if there is at all any reaction between A and B, then we produce an edge. For example, in this reaction mechanism, A reacts is A in the reaction somehow A and B are there is some reaction happening between A and B. There is some reaction happening between B and C and D, C and B. It can be that C is forming into B and A is forming into B, and also there can be some reaction between D and B, and as a result they are related. Here it suggests that the B and D are very strongly related. It is a very important reaction because of certain reasons, and which is represented by the width of this arrow. Of course, there is no connection between A and E, and as a result there is no arrow between A and E also, but there is E and F are being connected to each other. Okay. So, the idea is that it can be quantified by defining this by this relative error parameter, which is the summation over k equal to 1 to k. If you remember the detailed reaction scheme for the kth reaction, it was something like this: summation I is equal to 1 to n for the kth reaction we could have written like this. So, for the A, this was a generalized representation. So, A is the stoichiometric coefficient, omega is the reaction rate constant, and this parameter we will see that how this delta is defined. This delta is defined that if this is basically is equal to 1 if there is a kth elementary reaction involves species B and it involves 0 otherwise. So, you see that this numerator contains this summation from k is equal to 1 to k, which is k is the reaction number. So, it considers all possible reactions in which A and B can be involved, and this is the stoichiometric coefficient of A in the reaction k. It is the reaction rate of k, and this is the delta parameter which is defined here, and on the denominator we have essentially the stoichiometric coefficient of A and times the reaction rate of k. Okay. So, essentially you see that if all involved reaction if all involved of reactions of A involves B, then it becomes then this parameter essentially becomes 1, and this RAB is equal to 1, okay, in the extreme limit. On the other hand, if none of the reactions involves B, then it becomes 0. So, this parameter essentially ranges between 1 and 0 or between 0 and 1. Okay. So, basically this tells you that if you remove the species B, that what amount of error you will induce. Okay. So, if this reaction if the reaction between between A and B, if B is participating in all reactions involving A, then of course it will introduce a huge error. But if this is not participating in very many reactions involving A, then the amount of error introduced will be small. Okay, that is what this is saying, and using that we can essentially compute this RAB for different parameters, and this is how it looks like. That this is the threshold value. We can basically then set a threshold of RAB, that we can say that we will want to make a reaction mechanism in which we will consider all our species which has a threshold which will involve reactions between which has a threshold value of greater than which has a threshold value of greater than 0.1. Okay. So, and if we see that that if this is essentially the ethylene reaction mechanism, we will see that this is how it looks like, that, and often it happens that this reactions happen in groups. So, for example, if we set here a threshold to be about 0.2, we will see that this will involve a reaction which is 33 species and 205 elementary reactions. On the other hand, if you want to set a very low threshold, that is, we want to have a very little error, we will need about 70 species and 463 elementary reactions. So, this gives us an idea about how to systematically reduce reactions and arrive at smaller reaction mechanisms using this DRG relation, and how we can arrive at a skeletal mechanism from a fairly complicated and a detailed reaction. So, that is all for this topic of oxidation mechanism of fuels, and we will come back next with to discuss about transport phenomena. So, all these reactions as we have discussed are basically except for one little bit of discussion where we try to identify the difference between the initiation reactions between a homogeneous system versus that in a flame. We have not considered the effect of diffusion, but as you know, in practical systems diffusion is very important, and we need to understand what are the processes that control it and what are the parameters or the parameters that define diffusion, or whether the diffusion will happen fast or slow as such, like that. So, that is all for now. Thank you very much.